This video is about taking the derivative of a product of functions. But before we start that, let's just review our terminology. When we have a function y equals f of x, the derivative comes from the slope of a secant, and we take the slope of the secant, we take the limit of that slope until the points that make the secant are infinitely close. So to be perfectly clear, we think of any function f of x. We can have 2 points on that function, even though we have no idea what the function is. So we can have a point at any value x, and the y value is f of x. And then any value that could be close to it, x plus some amount a, and the function at x plus a, f of x plus a. So then the slope of the secant is the difference between the y values, f of x plus a minus f of x, divided by x plus a minus x, which is just a. And then to turn the slope of a secant into a derivative, which is the slope of the tangent, we have to make a get infinitely close to 0. So we take the limit as a goes to 0 of the slope of this secant, and that's what we call dy dx. And that's not dependent upon calling all functions f. If we had a function g, the same thing would be true, but it would be g of x plus a minus g of x. And we would take the limit as the slope of its secant changed when a got infinitely close to 0. Okay, so now let's get to the problem at hand. We're going to look at a product of functions, 2 functions, f of x and g of x. And we're going to change what we call them here because it's a little inconvenient to call all the derivatives dy dx when you have different functions. So we're going to call the derivative of f prime of x. That's what this f apostrophe x means. And we're going to call the derivative of g of x g prime of x. Again, we use this little apostrophe to mean prime. There's still dy dx in terms of the y that's equal to that function, but we can tell what derivative we're talking about much more easily this way. So suppose we want to look at a product, any 2 functions, f of x and g of x. We want to know what's dy dx in this case. Well, if we use our definition of derivative, it's the function at x plus a minus the function at x divided by a. Remember, in this case, our function is a product of 2 other functions. This is the product of those 2 functions at x plus a minus the product of those 2 functions at x over a. This is the slope of a secant. Then we take the limit as x plus a gets infinitely close to x, which means a gets infinitely close to 0. And that gives us the slope of the tangent, the derivative. Now, I'm going to show you the answer before we do the algebra to derive the right formula. I'm just going to show it to you because I think it's important to know where we're going when we have to do so much algebra to get there. So here it is. The derivative of a product, when you have f of x times g of x, is the sum of 2 terms. G of x times the derivative of f plus f of x times the derivative of g. Notice each term has one of the functions plain the way it sits without taking the derivative times the derivative of the other. G times the derivative of f plus f times the derivative of g. Now where does this come from? Well, it comes from this definition, and we use a little algebra trick to get started. So first let's just describe the trick. I can take this already complicated expression and change it, but leave the result virtually unchanged by subtracting and then adding the same thing. So I'm calling the same thing any blob. So when I subtracted, I made it blue, and when I added, I made it red. But it's the same thing. I subtract something, then I add that something back. I do that to introduce a term to help me change this expression, to turn it into this lovely formula. So let's see what I do. What is the any blob? Well, in this case, any blob is going to be the function g at x plus a times the function of f at x. So we subtract g of x plus a times f, and then we add g of x plus a times f. So we didn't change anything. Now you're going to see why we did that. We did that so that in the first two terms, I could factor out the g of x plus a. See? Whoops. We have a g of x plus a here, and we have a g of x plus a here, and I'm going to factor it out here. And in the second two terms, I'm going to factor out the f of x. I have an f of x in each term. I'm going to factor it out. And if you look at this closely, very closely, you'll notice I have this g of x plus a times what kind of looks like the derivative of f, plus f of x times what kind of looks like the derivative of g. We have to separate the terms to see if this works. And we're actually going to use the limit laws to justify what we do. But first, I'm just going to separate them out. I'm going to look at these first two terms. It's a product here, right? So I'm going to make it g of x plus a over 1 times this slope of the secant on f. Plus, now we have a plus here so we can separate them into two fractions, and this part's a product. So f of x over 1 times what is clearly the slope of the secant at g. And if you look at this closely, you can multiply to get back to this. We can multiply these two, the new denominator is a, and g of x plus a is multiplied by this difference. And the same thing here, the denominator 1 times a is a, and we can multiply by that difference. Well, now that we have a product plus another product, we can remember the limit laws and take the limit of each part. So the limit of a product is the product of the limits. The limit of a sum is the sum of the limits. And finally, the limit of this product is the product of the limits. And if you look at this very closely, well, the limit of g of x plus a as a goes to 0 is just g of x. That's really easy. And the limit of f of x as a goes to 0 is just f of x. And these are just the derivatives. We're basically at our formula. It's an abracadabra moment. We can write all of these and show you. But in fact, you might have to watch this a couple of times in order to see it. I have to move this little image over here so that I am not in the way of what I'm trying to show you. The limit of g of x plus a as a goes to 0 is g of x. There it is. The limit of f of x plus a minus f of x over a as a goes to 0 is the derivative of f of x, f prime of x. The limit of f of x as a goes to 0 is just f of x, because there's no a here to change. And the limit of g of x plus a minus g of x divided by a as a goes to 0 is the derivative of g. So we just proved our formula. Well, as I said, that might bear watching again. But before we go away, let's recognize that we could write this in either order. Addition is commutative, so it doesn't matter which of these terms you put first. And let's just do one example quickly. So suppose we have a product, x cubed times sine of x. Let's call x cubed f of x and sine of x g of x. So we know we need each function and its derivative, so let's just figure them out. F of x is x cubed and f prime of x is 3x squared. G of x is sine of x, so g prime of x is cosine x. We just fill in this formula. And we get x cubed times cosine f of x times the derivative of g plus g of x sine of x times the derivative of f. You're going to have to practice this a lot, and you may have to watch this video more than once, but it's pretty straightforward, and now we can multiply any two functions, and you can find the derivative.